So the next thing I have to discuss is solving partial differential equation. Using Fourier transform. Okay, so this is here we come back to Fourier transform. Okay, we can solve partial differential equation using Fourier transform. Okay, so we already discussed in the properties as well as in working out the problems. We know that the Fourier transform of d by dx of f of x, right, is equals to minus is times Fourier transform of f of x, right? So this we have already discussed. We can also extend this formula for nth order differentiation. Therefore we can write the Fourier and can be written as Fourier transform of f of f of d power n divided by dx power n of f of x equals to minus is times whole power n, right, f of x. Okay, so this is a Fourier transform. Okay, suppose if our function, this f of x is a function of x and t. Okay, suppose if our function is a function of two variables, then suppose if I call this as u, okay, instead of f of x, and u is a function of x and t, then the Fourier transform of, okay, we are using the same formula. However, instead of this ordinary differential equation, we have to use partial differential, okay, because u is now a function of x as well as t. Okay, so if I partially find the partial derivative of nth order partial derivative of u with respect to x, okay, and if we take the Fourier transform, okay, if we take the Fourier transform, it is also equals to minus is times whole power n Fourier transform of our u. Okay, right, so this is the formula. So you don't need to remember all these things, just remember this one. So we usually solve second order differential equation. So for that we need for that we have n equals to 2. Okay, so therefore the Fourier transform of dou square by dou x square of u, okay, x comma t is equals to, here we have a 2, therefore minus I square becomes minus and s square, right, f of u is a function of t. Okay, so this is the one formula we will be using, okay, again and again. Similarly, this is a Fourier transform. Similarly, we have Fourier sine and cosine forms. Okay, so the Fourier and sine and cosine forms can be written as Fourier sine transform of dou square u by dou x square is equals to s times, okay, this u s times u of x comma t at x equals to 0. Okay, minus this is s square Fourier sine transform of u of x comma t. Okay, so here we have a new term. Okay, so remember, whenever it is nothing but this part, right? This is the s, okay, and this part alone is nothing but u of 0 comma t. Okay, so it's the value of the function u at x equal to 0 and for all times. Okay, so that's the meaning here. Okay, and similarly the Fourier cosine transform. Okay, Fourier cosine transform of dou square u by dou x square is equals to minus dou u by dou x at x equals to 0 minus s square Fourier cosine transform of u. Okay, here there is a slight change. Here we need u of 0 comma t, whereas here we need u prime. Okay, u prime of 0 comma t, where u prime is nothing but dou u by dou x. Okay, so whenever you are given in the problem, you will be given boundary value problems, where sometimes they will give u of 0 comma t, and on that situation you have to use Fourier sine transform, and in some other problems they will give u prime. Okay, u prime of 0 comma t. Okay, and in that situation you have to use cosine transform. Okay, this can be get clear as we work out the problems. Okay, let's try to solve this problem using Fourier transform. So this problem is in page number 965. Okay, so it may also ask me in the exam. So this is the heat conduction problem, and it's a second order differential equation. We have to solve this to find u. Okay, our aim is to find u which satisfies this equation. Okay, so they have given the conditions, okay, initial conditions and boundary conditions. So they have given that when x equal to 0, and so here u is a function of x and t. Okay, so we need to know the what's the value of u at the initial or at the end. Okay, then only we can solve this problem. So they have provided all these inputs. Okay, so they have told that the value of u equals to 0 when x equal to 0 and t greater than 0. Okay, therefore we can write at u of 0 comma t, okay, is nothing but 0. Okay, I am writing it through this equation. u equal to 0 when x equal to, this is the x part, when x equal to 0 and t greater than 0 for all times. Okay, and they also provided that u equals to u of x comma t equals to 1 when x is less than 1. Okay, when x is less than 1. So this is the first condition, and u of x comma t equals to 0, okay, when x is greater than 1. Okay, greater than or equal to 1. Okay, so these are the condition we will need when we are solving this equation using Fourier transform. Okay, so the given equation is dou u by dou t equal to dou square u by dou x square. Okay, so let me number this equation. So let's take Fourier. So here they have given u of 0 comma t. Okay, whenever they have given u of 0 comma t, we have to use Fourier sine transform. Okay, whenever they have given u prime of 0 comma t, then you have to use cosine transform. Okay, so in the problem, in the condition boundary conditions, they have provided u of 0 comma t. So we are going to use Fourier sine transform. Okay, so let's take f of s on both sides. Okay, both sides in equation 1. In equation 1. Therefore we have Fourier sine transform of dou u by dou t equals to Fourier sine transform of dou square u by dou x square, right? Therefore, what is Fourier sine transform? So this is our f of x now. Therefore, our Fourier sine transform is root 2 by pi integral 0 to infinity dou u by dou t sine sx dx equals to, and this side we have root 2 by pi integral zero to infinity dou square u by dou x square sine sx dx, right? And this Fourier sine transform of dou u by dou t is nothing but, we have already worked this out, so it's the first derivative. Okay, so we have to substitute n equal to 1, therefore we have a minus is. Okay, so we have to use sine transform. Therefore let me write it out. Fourier sine transform of dou u by dou t, okay, is equals to let me write it again. So here if you notice that here the integration is with respect to x, okay, and the differentiation is with respect to t, so we can take this dou by dou t outside. Okay, so we can write this as dou by dou t of root 2 pi integral 0 to infinity. Okay, here we have u sine sx dx. Okay, and on this side we know that the Fourier sine transform of any u function u can be written as is nothing but s into u of 0 comma t. So it's s into u of 0 comma t minus s square into Fourier sine transform of u of x comma t. Okay, and this is nothing but Fourier transform of, so dou by dou t, and this full part is nothing but, so here we have u, okay, and sine sx, and this integral is nothing but Fourier transform of u of x comma t, right? So this is a Fourier sine transform. Okay, and this side we have s into u of 0 comma t minus s square into same Fourier sine transform of u of x comma t. Okay, so for simplicity let me write this as u bar. Okay, u bar, where u bar represent Fourier sine transform of u. Okay, so therefore this equation can be written as dou u bar by dou t equals to s into u of 0 comma t minus s square u bar, right? So this is our equation, and also we have given that u of s comma t equals to 0. Okay, so it is given in the problem u of 0 comma t is 0. Okay, therefore we can substitute 0 here, and since this is 0, the whole term is 0. Therefore we have dou u bar by dou t equals to minus s square u bar, or dou u bar by dou t plus s square u bar equals to 0. Okay, so the second order equation becomes a first order equation, and we have a, so it's a linear first order equation. This is a linear first order equation, ordinary differential. Okay, OD first order differential equation. And we have a general solution for this equation, and it is u bar equals to a into e power, let me write it in a more general way, any function of this form. Okay, any function of this form, dou x, okay, dou x by dou t plus k, okay, some constant k, x equals to 0, then the general solution. Okay, general solution is x equals to some constant a into e power kt. Okay, so it's minus kt. So this is the general solution. So this equation also looks similar to this equation, so we can write the solution for this equation as u bar equals to a into e power minus, okay, instead of k we have s square here, therefore s square, and the derivative is respect to t, therefore we have t here. Okay, so this is our general solution. So now we have to find a, okay, in order to find u bar. Okay, for that we need some inputs. Okay, so what's our u bar? So we defined u bar. Okay, it's, let it be equation 2. Okay, and our u bar is nothing but the Fourier sine transform of u of t x comma t. Okay, we also know u bar equals to Fourier sine transform, Fourier sine transform of u of x comma t. Okay, and what is the Fourier sine transform? Therefore it is nothing but root 2 by pi integral 0 to infinity u of x comma t sine sx dx, right? Therefore our u bar is nothing but root 2 by pi integral 0 to infinity and u of x comma t, okay, sine sx dx. Okay, so let's split this this integral into two parts. Therefore we have let me take this root 2 by pi outside, and integral from 0 to 1, okay, u of x comma t sine sx dx, okay, plus integral 1 to infinity. Okay, so I am splitting this integral from 0 to infinity as 0 to 1, and from 1 to infinity u of x comma t sine sx dx. Okay, so there is a reason, because we know that our u of x at t equal to 0, they have given that when t equals to 0, our u of x comma t equals to 1 for x less than 1. Okay, so and it is equals to 0 when x greater than or equals to 1. Okay, so let's try to find our, so when t equals to 0, we know that u of x comma t equals to 1 for x less than 1. Okay, and u of x comma 0 equals to 0 for x greater than or equals to 1. Okay, therefore here the integral runs from 1 to infinity, therefore our u of this term will become 0 by definition. Okay, when t equal to 0. Therefore let's try to find, so this is our general u bar of x comma t. Okay, so we are now finding u bar of x comma 0. Okay, therefore we have root 2 by pi. So since we are finding at time t equal to 0, here also we have t equals 0, and if we apply this condition, this integral will get vanished. Okay, or let me rewrite this so it will be clear. Okay, so it's integral 0 to 1 u of x comma 0 sine sx dx plus integral 1 to infinity u of x comma 0 sine sx dx. Okay, and this becomes 0 by this condition. Okay, by this condition, and it is given already. Okay, therefore this integral alone exists, and it is, and here is u of x comma 0 is 1. Okay, for x less than 1. Okay, therefore we have root 2 by pi integral 0 to 1, and instead of u of x comma 0, let me write it as 1. Therefore we have sine sx dx, and therefore we have root 2 by pi. Our sine sx is minus cos sx by s, and it's from 0 to 1. Okay, so upon substitution of the limit, we have root 2 by pi upper limit. So if we substitute upper limit, we have minus cos s by s, and if we substitute lower limit, minus, and this minus becomes plus, and the cos of 0 is 1 divided by s. Okay, and we can rewrite this as root 2 by pi 1 minus cos s divided by s. Okay, and this is our u bar of x comma 0. Okay, at time t equal to 0. Okay, and from equation 2, we know that u bar of x comma t equals to a e power minus a square t. Okay, here if we substitute u bar of 0 at the time t equal to 0, therefore we have a into e power minus s square into 0. Okay, instead of t, let me put 0. Therefore we have, so this be equation 3, and here we have a into 1. Okay, therefore u bar of x comma 0 equals to a. Okay, and this be equation 4. Okay, therefore comparing equation 3 and 4 we have a equals to root of 2 by pi, because here also we have u bar of x comma 0 and here also we have u bar of x comma 0. So if we compare, then we can equate a equal to root of 2 by pi 1 minus cos s divided by s. Okay, so let this be equation 5. So let's substitute this value of a in equation 2. Okay, so substituting value of a in equation 2, we have u bar of x comma t equals to, instead of a, let me put it as root 2 by pi 1 minus cos s divided by s into e power minus s square t. Okay, so this is our this u bar. So this is a Fourier, this u bar is nothing but Fourier sine transform of u of x comma t. Okay, and this is equals to root 2 by pi, this u bar is 1 minus cos s divided by s into e power minus s square t. Okay, so our aim is to find u of x comma t, not the Fourier cosine transform. So that we have to take Fourier inverse. Okay, if we take Fourier inverse, we have u of x comma t is equals to root 2 by pi integral 0 to infinity, okay, 1 minus cos s divided by s into e power minus s square t into sine xs ds. Okay, so this is taking Fourier inverse Fourier transform, inverse Fourier sine transform. Okay, so we end up with this equation. So this is our solution. Okay, so this is the solution. Okay, so we have solved this problem. Our aim is to find u of x comma t, and we have find it as u of x comma t is nothing but root of 2 by pi integral 0 to infinity and this term. Okay, so let me again work out another example where we can apply Fourier cosine transform. So this is the next example. Okay, here also we have to find u. So the given differential equation is dou u by dou t equals to k times dou square u by dou x square. Okay, and they have provided some conditions. Okay, so the first condition is u of this for at t equals to 0, u of x comma t. Okay, instead of t we have to put 0 is equals to 0. The value of u at x comma 0 is 0. Okay, so they also provided for t greater than 0, u of x comma dou u by dou x of 0 comma t equals to minus a. Okay, where this is a constant. Okay, so these are the conditions they have provided. So we always look for either u of 0 comma t, okay, whether they have given u of 0 comma t or u prime of 0 comma t in our problem. Okay, so here they didn't give u of 0 comma t, instead they have given u of x comma 0. Okay, so this is time here it is space. Okay, this is x, this is x. So if we look another the next condition, they have provided the u prime. Okay, u prime of 0 comma t. Okay, so if this is the case, we have to take Fourier cosine transform. Okay, and this is Fourier sine transform. So in this example, they have given u prime of 0 comma t. So let's take Fourier cosine transform of these equations. Okay, let me number this equation as 1. Okay, and let's take Fourier cosine transform. Okay, on both sides of equation 1. Okay, so if we take Fourier cosine transform, then we have Fourier cosine transform of dou u by dou t. Okay, is equals to Fourier cosine transform of dou square u by dou x square. Okay, and since the Fourier cosine transform, the integral is with respect to x, we can take this t outside, dou by dou t outside. Therefore we can write dou by dou t of Fourier cosine transform of u of x comma t. Okay, you can write this as this way, and this Fourier cosine transform of dou u by dou x is, we have to substitute the formula. Okay, and the formula is, okay, for this part we have a formula which reads as minus dou u by dou x at t equals to, at x equals to 0, minus s square Fourier cosine transform of u of x comma t. Right, so this part is formula, this is this one. Okay, and this one. Okay, this comes from using the formula. Okay, we use the formula. Okay, and they have given that this dou u by dou x at x equal to 0, okay, is minus a. Okay, therefore we can write this as minus of minus a, this is equals to a. Okay, minus a. Therefore we have a minus s square Fourier cosine transform of u of x comma t, and this side we have dou by dou t of Fourier cosine transform of u of x comma t. Okay, for simplicity, let's write this as u bar. Okay, Fourier cosine transform as u bar. Therefore we have dou u bar by dou t equals to a into minus sorry, so I also forgot to put a k here. Okay, since we have in the equation we have k, I left this k, therefore I put k here, and we have k times. Okay, so k times this one, therefore we have ka. Okay, and before doing this, let's try to write it in an explicit form, in the integral form. Therefore we can write this Fourier cosine transform as dou by dou t of root 2 by pi integral 0 to infinity u of x comma t cos sx dx, right, equals to ka times ka into minus s square, okay, s square, we have a k because this k is common, okay, so we have a s square k, and the Fourier cosine transform of this one is nothing but root 2 by pi integral 0 to infinity u of x comma t cos sx dx, okay. So let's remove this, let's divide the whole equation divided by 2 pi, okay. So we have dou by dou t of, so let me write this integral as u bar, okay. So let me write this whole integral as u bar, therefore this also becomes u bar, okay. So if we write this as u bar, then we will have dou u bar by dou t, okay, because this full integral is nothing but our Fourier cosine transform of u of x. I am writing this as u bar, okay. So u bar equals to ka, okay, ka times minus s square k into u bar, okay. Here also we have u bar. So finally we have our equation dou u bar by dou t. I am taking this term, okay, the terms containing u bar to our left hand side, therefore we have s square k u bar equals to ka, okay. So let this be equation 2, okay. So this is also a standard differential equation, okay. It's an inhomogeneous equation and it has a general solution, okay. So any equation of this form can be written as, so the general form of this equation is dou y, sorry, dou y by dou x, okay, plus py equals to q. So this can be written as y into e power integral p dx, okay, p dx equals to integral q into e power integral p dx, okay, plus c, okay. We can write the solution as this form, okay. So this is a general equation. So this is general solution for the equation of this form, okay. If you look, our equation also looks similar. If we compare, we have t instead of x and we have u bar instead of y, and our p is nothing but s square k, okay, and our q is nothing but ka, okay. So let's try to form this. First try to find this integral p dx, okay. So for our case, p equals to s square k, okay. Therefore integral p p and dx, okay, and dx is nothing but dt, okay, in our case. Therefore we have p dx equals to integral s square k dt, right? And since this s square k is a constant, we can take this outside the integral. Therefore we have s square k in integral dt, okay, and the integral dt is nothing but is t, okay. Therefore we have integral p dx as s square kt. Therefore we can write our equation as, instead of y we have to put u bar. Therefore u bar into e power integral p dx. Instead of integral p dx we have s square kt, okay, equals to integral q, okay. So integral, and q, instead of q we have ka, integral q, instead of q we have ka into e power s square kt, okay, plus c, okay. So this integral can be solved. Since k is a constant, we can take so we can integrate this, and if we integrate here we have dt, okay, right, dt. Therefore we can write this as, we can take this k outside, and if we integrate this, we have, so we have to integrate e power s square kt by dt, okay. So integral e power s square kt dt, and we have a c here, and if we integrate this, we can have ka into e power s square kt divided by s square k, right, plus c, and this k and the k get cancelled, and we have a by s square e power s square kt, right, plus c, okay. And in this side we have u bar into e power s square kt, okay. So we are multiplying both sides by e power minus s square kt. Therefore we have u bar equals to u bar of x comma t equals to a by s square plus c into e power minus s square kt, because if we multiply both sides by e power minus s square kt, we have u bar into e power s square kt minus s square kt, okay. Therefore we have e power 0, therefore e power 0 is 1, so we left with u bar alone, okay. And here also we left, this term becomes 1 if we multiply by e power minus s square kt, and since we don't have an e power s square kt here, so this becomes c into e power minus s square kt, okay. So in order to find c, let's find the value of u bar of x comma 0, okay, at a time t equal to 0. At t equals to 0 we have u bar of x comma 0 equals to a by s square into plus, since we put t equal to 0 we have c, okay. So let this be equation 3, okay. This equation be 3, let it be 4, okay. And we know that u bar of x comma 0 is equals to since u bar is nothing but the Fourier cosine transform, right? Fourier cosine transform of u of x comma 0, right? And the Fourier cosine transform is root 2 by pi integral 0 to infinity, and this is u of x comma 0 cos sx dx. Okay, and we know that from the condition u of x comma 0 is 0. Okay, therefore this terms becomes 0, therefore our u bar of x comma 0 equals to 0. Okay, this is from the definition of u bar. Okay, we also have this here in equation 4. Okay, so let this be equation 5. Okay, so comparing equation 5 and 4, we have 0 equals to, instead of since we have u bar equal to 0, we put u bar equal to 0 here. We have 0 equals to a by s square plus c, right? From this we can find c as minus a by s square. Okay, and let this be equation 6. So substituting 6 in which equation? In equation 3 we have our u bar of x comma t equals to a by s square. So we can take this a by s square outside. We have a by s square, okay, plus, sorry, into c times we have c times c power minus a square kt. Instead of c we can put minus a by s square, therefore we have minus a by s square into e power s square minus s square kt. Okay, and we can take this a by s square as common, therefore we have a by s square of 1 minus e power minus s square kt, right? So this is our u bar. Okay, u bar of x comma t, which is nothing but Fourier cosine transform of u of x comma t into 1 minus e power minus s square kt. Okay, so we need u of t. So u of x comma t is the solutions. For that we have to take the inverse cosine transform. Okay, so taking inverse Fourier cosine transform, we have u of x comma t equals to a into integral 0 to infinity. Since s is a part of the integral, we have 1 by e power minus s square kt divided by s square, because this s square gets into this one, into, since we are taking cosine transform, cosine inverse transform, we have to use cos sx ds. Okay, for inverse transform the integration is with respect to s. Okay, for Fourier cosine transform we have dx, for Fourier inverse cosine transform we have ds. Okay, that is dx and this is ds. Okay, so this is our final result.